Today's class is the lecture 5 on magnetic materials. So in the previous class, we have discussed about the introduction to the magnetic property of substances, and we tried to classify materials into diamagnetic, paramagnetic, and ferromagnetic materials, and we also tried to understand ferrimagnetic material properties and we compared them. In the next lecture, we discussed about the classical Langevins theory of diamagnetic material, and also we derived the expression for Langevins theory, classical Langevins theory of paramagnetic materials, and in both cases, so we came to conclusion that diamagnetic property, that is susceptibility, is negative and independent of temperature. Also paramagnetic property, that is inversely proportional to temperature, and susceptibility positive. So we have observed in these two derivations, and today's class we will dedicate to the quantum mechanical treatment of paramagnetic materials. So we will be today discussing about the quantum mechanical treatment for paramagnetic materials. Now, so start with quantum theory or quantum treatment for paramagnetic materials. While discussing the classical theory, we observed that we could not make a clear differentiation between the para and ferromagnetic properties. According to classical theory, the atomic dipoles, they are allowed to have or permitted to have orientation in all possible directions. There was no restriction on the direction of orientation of the dipole, but quantum theory put conditions for orientation of atomic dipoles, and they are allowed to have only permitted the orientations which are satisfying the quantum conditions. So we start with the basic idea that you can just see okay, allowed. So you see that the atom has a nucleus at the center and electrons revolve around the nucleus. They orbit around the nucleus, and because of this orbital motion, the electron has a orbital angular momentum which is L vector. So it is a L, and along with the orbital motion, the electron also has a spin motion, so which spins about its own axis, that is a spin angular momentum. So therefore electron is endowed with two kinds of motion. So electron which is orbiting around the nucleus has orbital motion and spin motion. Because of orbital motion, there is a orbital angular momentum which is L, and because of spin, it is having spin angular momentum S, Therefore, you have two vectors L and S. They are L plus S is equal to J. J is also a vector, and so you know that L vector plus S vector. So we have a resultant vector J, which is called a total angular momentum vector. Total angular momentum vector J is L plus S. J along this direction, S is a vector, their resultant is J. So J is equal to L plus S. So L minus S means, so L, because it is vector, it will have both magnitude and direction, then J value will be small. So J total angular momentum is L plus S. See, you have the direction S is orbiting, this S vector is orbiting around the Z axis, then it will have a orientation in all directions, and then L, this is called precessional motion. So it is going around the J vector, S vector and L vector. S vector is going around here, L vector is here, L plus S together is J vector, and J is total angular momentum vector. So J is the total angular momentum vector, J is equal to L plus S. And if same thing is placed in a magnetic field, so now when an atom is placed in a magnetic field, then we have additional precession or additional orbiting of J vector. So the J vector along with S and L. So you see that S vector is orbiting here, L vector is orbiting here, their resultant J is L plus S. This also orbits around the Z axis, that is the external magnetic field B, applied magnetic, when the atom is placed in a external magnetic field B, the J vector, which is L plus S, resultant of L plus S, also precesses or orbits around the field along Z axis, that is the direction of field. So projection of J on this field is called Mj. This is what we are going to use in the derivation. So Mj is projection of J, total angular momentum, along the field axis, and J is L plus S. Now, with this brief introduction, now you can see that magnetic moment of atom, so which we have already derived in the previous equation, mu is equal to G mu B J. Mu is equal to G mu B J, and it is with a minus sign, and G is Landé G factor. When an atom is placed in a magnetic field, splitting of spectral lines takes place. That is given by G, that is Landé splitting factor or Landé G factor. Mu B is Bohr magneton. J is what we have seen, L plus S, that is total angular momentum quantum number, which is L orbital quantum number plus S spin quantum number is J. Therefore, magnetic moment mu is equal to minus G mu B J. When atom is placed in magnetic field, it will acquire energy, that is work is done. That work done or potential energy is equal to minus mu dot B. This is what we have used in our earlier derivation also. So this minus mu dot B is minus mu B cos theta, and U is minus G mu B J, therefore minus of minus, it becomes plus. For mu, we substitute G mu B J, it is B cos theta as it is. So then you rearrange the terms, G mu B B on one side and J cos theta on the other side. So J cos theta is nothing but the, so if you have a field direction and the magnetic moment mu is inclined at an angle theta with the direction, then the along field axis, its component is J cos theta. So J cos theta along y axis, and along x axis it is J sin theta. So the field is along z axis or along the axis. So that component we are taking as j cos theta, that is mj. So mj is j cos theta. So therefore g mu b mj into b is the expression for energy. U, potential energy, is equal to G mu B mj into B. Mj is J cos theta, which is component, vertical component of the magnetic moment. Now, for L is equal to 0, S is equal to half. So L is equal to 0 and S is equal to half. J is equal to L plus S. If you substitute L is equal to 0, S is equal to half, J will be 1 by 2. J is, you calculate for orbit L is equal to 0 and S is equal to half, J is also half. It means mj, which is projection, mj, which is projection of j along the field axis. It can have 2j plus 1 values. Mj can have 2j plus 1 values. So we have obtained j is equal to half. So it is 2j half plus 1. Mj, 2j plus 1 is 2. So the mj can have two energy levels. That is, atom, when it is placed in external magnetic field, it is split up into two energy levels for condition when L is equal to 0, S is equal to half. Now, so you can look at the splitting equation for electron. G is equal to 1 plus, this is a flower bracket from here to here. We have j into j plus 1 plus s into s plus 1 minus L into L plus 1 whole divided by 2j into j plus 1. So this is for the bracket only. So G, Landé G factor is given by an expression 1 plus j into j plus 1, s into s plus 1 minus L into L plus 1 whole divided by 2j into j plus 1. Now, so if you substitute for L is equal to 0, this first bracket or this bracket L into L plus 1 becomes 0. And once L is 0, then j will be equal to s. So j into j plus 1 becomes same. S is also j, so it is also j into j plus 1. So j into j plus 1 plus j into j plus 1 is 2j into j plus 1 divided by 2j, j plus 1 is 1. Therefore, 1 plus 1 is equal to 2. So I repeat once again. So for electron, the Landé G factor is equal to 2. How? First put L is equal to 0, this bracket becomes 0. And put S is equal to j, this becomes j into j plus 1, j into j plus 1. So this is 2j into j plus 1 divided by 2j into j plus 1 is 1. So 1 plus 1 becomes 2. So for electron, G is 2, and from the equation 2, that is potential energy G into mu B mj into B. So energy of two levels, one is higher level, another is lower level. We will calculate. For higher level, mj has two values, plus half and minus half. For higher level, mj is equal to plus half. For lower level, mj is equal to minus half. We substitute in the expression G mu B mj B. G is 2 mu B, B is the field, and mj is half, plus half. So therefore, half 2 goes, it is plus mu BB for higher level. So this spectral line splits up into 2, 1 and 2. So this level, upper level, is plus mu BB. That is, magnetic moment is positive in the higher level. So in the lower level, mj is minus half, then U becomes minus mu BB, lower level. Thus, the energy level is split up into 2. This is negative magnetic moment, this is positive magnetic moment. Now, let N be the total number of atoms in a paramagnetic material, of which some are aligned parallel and some others are aligned anti-parallel to the applied magnetic field. Suppose there are n number of atoms in a paramagnetic material, of which n1 number will be aligned parallel to the direction of field, n2 will be aligned anti-parallel to the direction of field. Therefore, n is equal to n1 plus n2. Then magnetization is m is equal to n1 mu plus n2 mu. N1 mu into N2 mu, and in the other direction it is negative. Therefore, N1 minus N2 mu. In the upper state it is positive, in the lower state it is negative. Therefore, it is minus N2 mu. So, therefore, N1 minus N2 into mu, magnetization. Now, you put the condition S is equal to half, L is equal to 0. In the expression mu is equal to G mu B J. So, this is equal to mu B, because mu becomes mu B, which is a Bohr magneton, because G is equal to 2, J is equal to half. Therefore, magnetic moment becomes mu B, mu suffix B. It is a Bohr magneton, basic magnetic moment of electron, one Bohr magneton. So, number of atoms in the lower state can be obtained by N1, that is equal to N0 e raised to mu B by KT. This is again applying the Maxwell-Boltzmann equation, Maxwell-Boltzmann statistics. The number of atoms in the lower state N1 is equal to N0 e raised to mu B by KT, and in the higher state is N2, that is again N0 into e raised to minus mu B by KT, because magnetic moment is minus here. So, put x is equal to mu B by KT. Then rewrite the equation. N1 becomes N0 e raised to x, because mu B by KT is equal to x, and N2 is equal to N0 e raised to minus x, because N2 is e raised to minus mu B by KT. Then N is equal to N1 plus N2. So, N0 is common. So, N0 e raised to x plus N0 e raised to minus x. You take N0 outside, then e raised to x plus e raised to minus x. Now, N1 is equal to N0 e raised to x, N2 is equal to N0 e raised to x, N is equal to N1 plus N2, N0 equal to e raised to x plus e raised to minus x. Now, we have to calculate fractional population, that is upper state is N1 divided by total number of atoms is N, lower state is N2 divided by N. So, N1 by N. So, N1 by N is fractional population, number of atoms in the lower state divided by total number of atoms in the substance, paramagnetic substance. N1 by N is equal to N1 is e to the power of x, because N1 is equal to N0 e raised to x, and N is equal to N0 e raised to plus x plus e raised to minus x, because we have N here. So, N is equal to N0 into e raised to x plus e raised to minus x. N0 cancels. So, N1 by N is equal to e raised to x by e raised to x plus e raised to minus x, where x is equal to mu B by KT. And for N2, that is fractional population in higher state, N2 by N is equal to e raised to minus x divided by e raised to x plus e raised to minus x, because N2 is equal to e raised to N0 into e raised to minus x. Therefore, N2 by N is equal to e raised to minus x divided by e raised to x plus e raised to minus x. Now, we are arriving at a very important step now, that is magnetization. M is equal to N1 minus N2 into mu, because N2, the magnetic moment in the lower state is negative, magnetic moment in the higher state is positive. N1 mu minus N2 mu, therefore mu is outside, N1 minus N2. So, magnetization is M is equal to N mu into the N1 and N2, that is e raised to x by e raised to x plus e raised to minus x, minus N2, that is e raised to minus x by e raised to x plus e raised to minus x. On simplification, n1 mu into e raised to x minus e raised to minus x divided by e raised to x plus e raised to minus x. Then we all know that e raised to minus x minus e raised to minus x divided by 2 is sine hyperbolic x divided by e raised to x plus e raised to minus x divided by 2 is cos hyperbolic x. Therefore, sine by cos is tan hyperbolic x. So this is n mu e raised to minus x minus e raised to minus x divided by e raised to x plus e raised to minus x is sine by cos. This is equal to tan hyperbolic x. And m is equal to n mu tan hyperbolic x is a very important step, where x is equal to mu b by kt. So we simplify by applying a condition when x is much less than 1. When x is very, very small, mu b by kt is very, very small, then tan hyperbolic x is approximately equal to x. So tan hyperbolic x is approximately equal to x. So magnetization becomes n mu tan x. Magnetization becomes n mu x. So where x is mu b by kt. So this mu is mu square. So this is equal to n mu square b by kt, and also b is equal to mu naught h. So therefore magnetization m is equal to n mu square, mu naught h is b divided by kt. Now we want susceptibility. Therefore susceptibility is chi, chi. Susceptibility chi is equal to magnetization by h, m by h. Magnetic moment divided by magnetizing force. So susceptibility phi is equal to m by h. This is equal to m is n mu square mu naught h whole divided by k t and the h which is in the numerator. H, that is in the denominator. This h gets cancelled. Therefore it becomes n mu square mu naught divided by kt, which is equal to mu is equal to mu b. So from our previous expression, that n is equal to mu b square mu naught by kt is expression for susceptibility. So we can simplify by putting phi is equal to c by t, where c is all this put together, n mu square b mu naught is a constant which is called Curie constant. So we arrived at a very simple expression, phi is equal to c by t. So which shows that the substance is paramagnetic property, that is chi is first positive and it is inversely dependent on temperature. So it is the property of the paramagnetic property of materials. This is for a particular case when L is equal to 0, S is equal to half. Up to this, it is the quantum derivation, quantum theory of paramagnetic substances. So you may be also asked sometimes for general case. Suppose if the L is equal to 0, mj is a projection of j, total angular momentum, along the field axis. If mj is 2j plus 1, that is 2 values, then only 2 energy levels will be there. That is what we have discussed so far. That is mj equal to plus half, mj equal to minus half. In case, if it is a general case, then mj can have 2j plus 1 values. So in that case, the equation becomes slightly complicated, but we are not going to derive it, but we will just extend and try to write the final expression. So that expression is for general case where mj is not just L is equal to 0 and S is equal to half. That is a limiting case. For general case, mj, if it has 2j plus 1 values, then there will be 2j plus 1 energy levels. In that case, the magnetized expression mj becomes m, n, that is total number of atoms, g, Landé G factor, mu b, that is the magnetic moment, mu is equal to mu b, that is Bohr magneton, into a special function, that is bj into x. So this bjx is called a Brillouin function. So this is a new function we are introducing here, this Brillouin function bjx. So magnetic moment in case when mj has all the 2j plus 1 values, then the atom will split into the energy levels of the atom when placed in external magnetic field will split into 2j plus 1 levels. Earlier we have seen limiting case when L is equal to 0, S is equal to half. There were only two, one plus mu bb, the another one was minus mu bb, one lower state, another upper state. Now in this case there are 2j plus 1 values. It is a general condition where this bj is given by 2j plus 1 by 2j cot hyperbolic 2j plus 1 by 2j into minus 1 by 2j cot hyperbolic x by 2j. So this is the expansion of the function bjx, and this also will simplify for limiting case when x is less than 0. Cot hyperbolic function is 1 by x plus x by 3 plus the further terms. So we take only first two terms. So which gives bjx is equal to j plus 1 x by 3j. So on simplification we directly get the Brillouin function as j plus 1 x by 3j. This is a simple direct step. Now with this we can write expression for susceptibility. X is equal to where x is mu b by kt and mu is g mu b b, that is g square mu b square b by kt. So substituting this in our previous equation we get magnetic moment n j into j plus 1 g square mu b square b by 3 kt. So chi is m by h. Chi is susceptibility, it is m by h. So this expression, that is n j into j plus 1 g square mu b square into mu naught by 3 kt. So this becomes, we put one simplification, that is g into j plus 1, that is put g into j plus 1 as p square. So p square is another term that we are introducing, this as effective Bohr magneton. To make the equation simple, so we are introducing p square. Now p square for g square into j plus 1. So n p square mu b square mu naught by 3 kt. Once again all these constants put together, susceptibility is m by h, so it is c by t, where c is given by n p square mu b square mu naught by 3k, where c is a Curie constant. So in these steps, so I will repeat. For particular case, L is equal to 0, S is equal to half, mj has only 2, so therefore there are only two energy levels, atom energy levels split into two, one is plus half, another is minus half. So one is plus mu bb, other is minus mu bb, that is the energy. So in general case, if there are mj has general 2j plus 1 values, the atom when it is placed in external magnetic field will have 2j plus 1 energy levels. It will split up into innumerable 2j plus 1, the large number of energy levels. So which is given by a general expression, magnetization m is equal to n, that is total number of atoms, g is Landé G factor, mu b is Bohr magneton into bjx, a new function which is called Brillouin function, whose expansion is 2j plus 1 by 2j cot hyperbolic 2j plus 1 by 2j into 1 by 2j cot hyperbolic x by 2j. So we can simplify this by putting x, when x is very small, less than 1, then cot hyperbolic x can be 1 by x plus x by 3 plus plus plus. So which gives bjx is equal to j plus 1 into x divided by 3j. Substituting this in our previous equation 5, so magnetization m becomes m into j into j plus 1 g square mu b square b by 3 kt, and this chi, which is susceptibility, is m divided by h. Therefore, n j into j plus 1 g square mu b square 3 kt by h. So b is mu naught h. Therefore, mu naught here is coming, h and h cancel. So therefore, we put g square into j plus 1 as p square, which is effective Bohr magneton. Therefore, chi susceptibility becomes n p square mu b square mu naught by 3 kt, and we can further simplify by writing susceptibility chi is equal to m by h equal to c by t, where c is all these terms, that is n p square, which is effective Bohr magneton, mu b square mu naught by 3k. C is